Hello everyone, my name is Proctor, and today we're going to be talking about the analysis of variance in linear models project. And we're basically using this TIP CSV dataset to answer this question. So just quickly glossing over it, we have our total bill, the tip, the gender, whether or not they were a smoker, the day of the week that they had received this tip, the time, and also the size of the people who ordered food. And so let's quickly go over or just summarize what the code is doing here. So we're loading the data set, printing the first few rows of the data set. Then we're going to conduct an ANOVA test to see if there's a significant difference in tips based on the day of the week. Print that ANOVA summary. Visualize the distribution across different days using our box plot, and then display a summary of the regression model. So let's quickly talk about the results that are presented here. So our ANOVA results show that there's no statistically significant difference in tip amounts across different days of the week. We have a p-value of 0.17, and this is greater than our threshold of 0.05. And so our box plot here confirms this by showing the tip distribution across days, and our regression analysis suggests that none of the days, Saturday, Sunday, or Thursday, significantly influence the tip amount compared to Friday, as their p-values are above 0.05. The r-squared value of 0.02 indicates that only 2% of the variation in tips is explained by the day of the week. And so overall, both ANOVA and regression suggest that the day of the week does not have a significant impact on our tip amount. So let's quickly go over our report. So just a quick summary. We basically we're trying to determine if the day of the week affects tip amounts. The ANOVA test shows an F statistic of 1.656 and a p-value of 0.1736, and this means there's no significant difference in the mean tip amounts across the days of the week. And so our box plot of tip distribution also supports this. We showing some variation, especially with a few high outliers on Sunday or on Saturday, but the medians are generally similar. Our linear regression model also confirms that the day of the week explains only 2% of the variability in tips, with none of the days being statistically significant. And overall, the analysis here suggests that the days of the week has little to no effect on tip amounts within this tip data set. Let's quickly go over our second task. So what this code is doing is we're going to load our data set as before, and then we're going to convert the categorical variables into binary values for our analysis, basically converting female for 1, male for 0, yes for 1, no for 0. Then we're going to define the independent and dependent variables for our regression model. Then we're going to add a constant term for our independent variables, and then we're going to fit a linear regression model and then print a summary of that model. We're going to plot the relationships between the total bill and the tip amount with the regression line, and then we're going to visualize the residuals of the linear model. So let's go over our results very fast. So our linear regression analysis shows that the total bill is a significant predictor of the tip amount with a p-value less than 0.001. The r-squared value of 0.469, this suggests that there's about 47% of the variability in the tip amount that can be explained by the total bill, the size, the sex, and the smoker status are independent variables. However, there are other variables like sex and size and smoker status have p-values greater than 0.05. And this means that they are not statistically significant in predicting the tip amount. The plot of total bill versus tip right here, this shows a positive relationship with the tips increasing as the total bill is increasing. Our residuals versus fitted values plot indicates some non-linearity, which might suggest that the model could be improved by addressing this issue. Our report here. So our linear regression model is aiming to predict tips amounts using total bill, group size, sex, and smoking status as our independent variables, and our model explains about 40% of the variation in tip amounts as shown by our R-squared value. Our total bill had a significant positive impact on tips, meaning that the higher bills tend to result in higher tip amounts. Our group size also had a positive effect, with larger groups leaving bigger tips. However, sex and smoking status did not have a significant influence on what the tip amounts were. Our residuals versus fitted values plot showed that there are no major issues, and this indicates that the model assumptions were met. And so overall, our model here, driven primarily by our total bill and our group size variables, is effective in estimating our tip amounts. Here we're going to, for task 3, we're going to talk about assumptions and limitations of ANOVA and linear models and how they can affect the validity of our results. So let's go through our code. So what we're doing here is, of course, we're loading the data set. We're going to perform an ANOVA to see if the tips vary by day of the week. We're going to visualize the tip distribution by day. We're going to test for normality of residuals using our Shapiro-Wilk test. We're going to test for equal variances using our Levene's test. Prepare the data for the regression analysis. Define the independent and dependent variables. We're going to add a constant term to the independent variables and then fit the linear regression model. We're going to visualize our regression between total bill and tip amount using our regression plot, and then plot our residuals to check for homoscedasticity using our residual plot. And then test for homoscedasticity using our Brewis-Pagan test, and then check for multicollinearity using our VIF. And so after that, we're going to apply some solutions. So we're going to apply our logarithmic transformation to the tip column for normalization purposes. Then we're going to perform our ANOVA again on the log transform tip values. And then we're going to evaluate whether residuals follow a normal distribution after our log transformation. And then if the Brewis-Pagan test indicates that we have homoscedasticity, we're going to use robust standard errors. And then print the linear regression summary with our robust standard errors. Let's quickly go over our results here. So our ANOVA test shows a p-value of 0.1736, and this indicates no significant difference in tip amounts based on the day of the week. The Shapiro-Wilk test is less than 0.05, and this confirms that the data is not normally distributed, and this violates one of the ANOVA assumptions. However, our Levene's test suggests the assumption of equal variance across groups is satisfied with the p-value of 0.64. And then we have our linear regression analysis, or OLS, model, which has an R-squared of 0.469, and this means that around 47% of the variability in tip amounts are explained by our independent variables we specified. The most significant predictor is the total bill, which is less than 0.001, and this has a positive relationship between total bill and tip amount. We have a sex and smoker status. These variables do not have a statistically significant impact on the total tips. Our residuals and homoscedasticity. Our residuals versus fitted values plot shows some patterns, and this indicates some tissue issues with homoscedasticity. The Brewis-Pagan test supports this with the p-value that suggests heteroscedasticity is present here, and this implies that robust standard errors may be needed to improve the model. we have our variance inflation factor, and the values are all below 5, and this indicates that there's no significant multicollinearity between the independent variables. And then we have our logged, transformed ANOVA, and robust regression. So after applying a log transformation to the tip amount, our Shapiro-Wilk test on the transformed data shows improved normality with a p-value greater than 0.05. And additionally, performing our linear regression with robust standard errors accounts for heteroscedasticity issue, and this improves the reliability of the results without drastically changing the model's coefficients or any of the conclusions. So let's look over the results that we had gathered from this analysis. And so our ANOVA linear regression analysis provides useful insights, but also reveals that there are limitations on the assumptions of both models. Our ANOVA assumes that the residuals are normally distributed, variances are equal across the groups, and our observations are independent. Our Shapiro-Wilk test indicates that the residuals are not normally distributed, and this is because the p-value is less than 0.05, and then this violates the normality assumption. And so in order to address this, we have transformations like the log or square root that can be applied to the dependent variable, and this improves normality. Our Levine's test, this confirms the equal variances assumption was met. If it had not been Welch's ANOVA, we could have used Welch's ANOVA as an alternative, and this ensures independent observations is also key to maintaining unbiased results. For our linear regression, our key assumptions include linearity, homoscedasticity, normality of residuals, and no multicollinearity. Our model showed a good fit with the total bill as a significant predictor of tip amount. However, our Brewis-Pagan test indicates issues with homoscedasticity, meaning the variance of residuals was not constant. And so in order for us to address this, robust standards errors were applied, which improved our reliability of the regression results. Our VIF values showed no significant multicollinearity, and this confirms that the predictors were independent. And overall, applying log transformations did help address normality issues, and using robust standard errors can improve model reliability in cases of unequal residual variance, and these corrective steps make the models more dependable, leading to stronger and more valid conclusions. So for our final task, we have a mini project that combines the ANOVA and linear models to make predictions, and so we'll quickly go over this one. This actually uses the same code from before, except we're not performing our transformations or our solutions. And so I'll just quickly go over our report since it's the same code and it would output the same results on the same data set. And so our little mini project here is analyzing how the day of the week and the variables such as the bill, the party size, the sex, and the smoking status affect the tip amounts using ANOVA and linear regression on a tip dataset. Our main goal here is to determine if tips vary by day and how other factors predict the tips. And our ANOVA results with the p-value of 0.1736 indicates that there's no significant variation in tip amounts across different days. However, our Shapiro-Wilk test reveals that the data is not normally distributed, and this violates the normality assumption of ANOVA. Our Levine's test confirms equal variance across days, and we have a box plot that shows similarity tip distributions, though there are outliers on Saturday. In our regression model, the total bill and the group size significantly predict the tip amounts, and this shows a positive relationship. The regression plot displays a clear upward trend between tips and the total bills. However, the The residuals plot suggests possible nonlinearity, and the Brewis-Pagan test indicates heteroscedasticity, and this means unequal variance in our residuals. And so despite the fact that we have these issues, our variance inflation factor confirms that there is no multiclinearity between the variables. And our analysis highlights violations in model assumptions such as homoscedasticity and normality, which could result in biased conclusions. So our solutions include data transformations, using robust errors, and addressing nonlinearity. And so our little mini project here provides underscores. It basically underscores the importance of checking assumptions and showing how we can use Python to aid in our statistical analysis. Thank you for listening. That is all.